Tier 5 creates a real-time virtual replica of the terminal ecosystem. It links yard operations, vessel schedules, truck arrivals, and equipment availability. The twin enables predictive optimization and what-if analysis before execution. Operationally, this helps avoid reactive reshuffles by anticipating bottlenecks and schedule changes. This slide shows the digital twin architecture for integrated terminal optimization. Operationally, the architecture matters because the twin depends on high-frequency data and consistent synchronization between the real terminal and its virtual model. Core components include real-time data ingestion, a simulation engine with synchronized replicas, an optimization coordinator for multi-objective planning, and a decision support interface. Operationally, these components connect container placement decisions to system-level outcomes like crane utilization, truck turnaround time, and vessel berthing delays. The example is Container Terminal Altenwerder at the Port of Hamburg. Data volume is over 1 million data points per hour. Assets include 15 automated stacking cranes, 88 automated guided vehicles, and 4 vessel berths. Optimization accounts for schedules, maintenance, congestion, and weather. Average reshuffling improves from 2.3 per container to 1.4 per container. Equipment utilization improves from 67% to 84%. Truck turnaround improves from 45 minutes to 32 minutes. Vessel berthing delays improve from 12% to 4%. Energy consumption shows an 18% reduction. Reactive movements reduced by 39%. Overall terminal throughput improves by 22%. Operators can test scenarios before implementation to avoid unintended congestion. Operationally, this is the difference between reacting to problems and preventing them. Tier 6 decentralizes optimization into a network of agents. Crane agents, stack agents, coordination agents, and prediction agents cooperate. Agents negotiate placement decisions using auctions and consensus mechanisms. Operationally, this allows local autonomy while still producing coordinated, system-wide reshuffling reductions. This slide presents the multi-agent ecosystem for distributed container reshuffling optimization. Operationally, the key idea is distributed decision-making with coordination. Each agent sees part of the system, but shared protocols allow the group to find stable, efficient outcomes. Emergent behaviors include load balancing across cranes and zones, anticipatory positioning based on predicted demand, resilient recovery under failures, and knowledge sharing across agents. Operationally, these behaviors reduce the need for constant, centralized retuning. The system adapts as conditions change. The example scale is 2.7 million 20-foot equivalent units per year. Assets include 24 automated stacking cranes and 102 automated guided vehicles. Reported reshuffling reduction is 31% versus centralized control. Reported operational efficiency is 94% even during multiple failures. Centralized control reports 2.1 moves per container and slow adaptation. Hierarchical control reports 1.8 moves per container and medium adaptation. Autonomous ecosystem reports 1.4 moves per container and fast adaptation. Reshuffling decreases by an additional 15% over the first year as agents learn. Tier 9 frames reshuffling as a quantum-ready optimization problem. The goal is to explore large combinatorial spaces efficiently. The formulation maps blocking penalties into a Hamiltonian with constraint penalties. Operationally, it is the same placement logic expressed in a form suitable for quantum optimization. Binary variables represent assigning a container to a stack and a position. Positions range from bottom to top within each stack. Blocking penalties depend on retrieval time differences. Operationally, you pay more when a placement buries an earlier retrieval under a later retrieval. This slide introduces the cost Hamiltonian term. Operationally, it is the part of the quantum objective that represents the reshuffling or blocking cost you are trying to minimize. This slide introduces the constraint Hamiltonian term. Operationally, it enforces feasibility by penalizing invalid assignments, such as multiple containers in one position or one container assigned to multiple positions. This slide shows a quantum approximate optimization, algorithm circuit concept for container reshuffling. Operationally, the circuit is a structured way to explore a large set of possible placements, combining cost-driven guidance with exploration. This slide begins the optimizer implementation. Operationally, focus on how the optimization problem is constructed from placement decisions and how the cost representation reflects blocking relationships. This slide continues the optimizer implementation. Operationally, focus on how constraint penalties are added so that solutions correspond to feasible yard placements. This slide continues the optimizer implementation. Operationally, focus on how the algorithm searches across candidate solutions and how it evaluates them. This slide continues the optimizer implementation. Operationally, pay attention to how results are obtained and interpreted. Quantum outputs must be decoded into concrete placement decisions. This slide completes the optimizer implementation sequence. Operationally, the key step is connecting the computed solution back to yard metrics, such as expected reshuffles and feasibility. The reported example is 20 containers across 4 stacks. Hardware is a 127-qubit quantum processor. The quantum approximate optimization algorithm uses 3 optimization layers. Classical exhaustive search is optimal but takes 45.2 hours. Classical heuristic is 89% optimal in 2.3 seconds. Quantum annealing is 94% optimal in 0.8 seconds. QAOA is 92% optimal in 1.2 seconds. The reported quantum advantage appears when the problem exceeds 15 containers. Current hardware limits. Solution fidelity, but scaling can be transformative. The interpretation notes that quantum search may reveal placement patterns that local classical methods miss, which matters for complex yards where the search landscape has many local optima. Tier 1 practice. 6 containers, 3 stacks, height 4. Formulate the integer program and compute the optimal reshuffle count. Tier 2 practice. Run the minimum blocking heuristic on the same instance. Show step-by-step penalties and compare the gap to optimal. Tier 3 practice. Genetic algorithm with population 50, crossover 0.8, mutation 0.15, tournament size 3. Run 100 generations and analyze convergence. Tier 4 practice. Define state, action, and reward for a Markov decision process and design a deep queue network. Tier 5 practice. Design a digital twin for 8 cranes, 20 stacks, and 5,000 containers per day. Quantify expected improvements and handle uncertainty. Tier 6 practice. Design a multi-agent auction mechanism for placement and describe adaptation under disruptions. For 6 containers and 2 stacks of height 3, define a quadratic unconstrained binary optimization, QUBO, and a quantum approximate optimization algorithm circuit. Discuss mapping to limited qubit connectivity and theoretical speedups. The point is to practice translating real constraints into an optimization form. Reshuffling is a major driver of terminal inefficiency and can reach 20 to 40% of crane moves. Tier 1 provides a complete model of feasibility and reshuffling costs. Heuristics and genetic algorithms scale to larger instances. Reinforcement learning adapts to dynamics. Digital twins optimize system-wide key performance indicators, and quantum methods explore future acceleration paths.